Wonderful. So hello all. Hopefully a lot of you remember, it wasn't that long ago. It was about 6 months ago, I think, that I was here last. And yeah, David, thank you for giving me that, giving that nice synopsis of some of the stuff I talked about. So today I will not go through all of that again, obviously. I'll just kind of give you a small review and an update on where we are and some of the issues that we're fighting basically when it comes to understanding why the sun is having these fits and starts. Just to touch on what David had mentioned, yes, regarding Mars, the idea that we're going to be colonized very, very soon is not, it's not realistic. And a lot of people do try to brush the whole concept of radiation and radiation storms under the rug. That's just one of the things that our sun does to us. And we're just beginning to learn, even as a space weather, the academic community, the physicists that we are, we're just beginning to learn how to deal with those types of things. But that is a completely different talk. So we can talk about, how this generation is kind of the Elmers to the Mars generation. We can talk about that later, but that will not be in this talk. So in this talk, actually, what we're going to talk about really is more along the lines of Aesop fables. Anybody remember the tortoise and the hare, hopefully from childhood? Because we are actually going to talk about the tortoise and the hare. I think it's actually a very useful tool to understand why the sun is doing what it's doing and how infuriating it is. And we'll get into that in just a second. And it's the funny thing is that nobody really talks about this. There's only one team in the world right now who really looks at the sun in the fashion I'm going to show you. And that's the McIntosh et al. Team. And I really think that they've got a big head start over a lot of the other dynamo models right now and prediction models right now, simply because they don't look at the sun as simply being a single entity, a symmetric entity. They look at it in terms of hemispheres. And so we'll talk about that more. And I'll go into it in more detail. I did talk about it last talk, but I don't think I went to it nearly as much detail as I will this time, because it helps explain what's happening. So the first, I don't know, maybe 7 or 8 slides are going to be a little bit of a review just to kind of warm us back up so that I can talk more in depth about what the sun is doing and has been doing recently, especially as about last year. But just to remind you, and I have not given a talk about this stuff yet, which maybe eventually I will if anyone's interested, that really space weather when it comes to Earth, there's really only about 4 different phenomena. I mean, there's a ton of things that the sun does, right? But really when it comes right down to it, there's only about 4 things that we really have to worry about affecting Earth. And the first largest thing, of course, that everybody knows are solar flares. And I think I stand on this side, don't I? Yes. So I can play this again. Everybody, I'm sure here knows what a solar flare is. If not, you've heard it. You've heard it on the bands because everything goes out, right? You've heard the radio blackouts that come from solar flares. This is basically the sun screaming. That's what I teach my students. It's like the sun screaming in electromagnetic light. And it goes from all wavelengths, all the way from, essentially X-ray, all the way down to the low end of the radio wave spectrum. And because of that, it's broadband emission. And depending upon the type of flare you're dealing with and where it happens on the sun, whether you're on the day side or the night side of Earth, you either hear it or you don't. And if it's launching a solar storm with it, that flare will actually last a longer time and its radio burst will actually be a little bit different. So a lot of times we can actually tell what is happening during a solar flare and whether or not a big solar storm will be launched with it, just simply based on the radio noise. But that's more of an academic thing. Now, along with solar flares, we have something called solar storms. Now, these are coronal mass ejections. They're not the same phenomena, and they don't have to happen together, these two, but they oftentimes do, and which is part of the reason why people get so confused, because they think a solar flare is a solar storm and vice versa. It's not. Solar flares are only electromagnetic light, so they reach Earth in 8 minutes. We have no warning at all. We can talk about probabilities of solar flares occurring, looking at the bad actors on the sun, but we don't necessarily have any way of predicting a solar flare, at least nothing that really works better than flipping a coin at this point. People like to think we do, but no, not really. And then there are solar storms. Now, these are coronal mass ejections. That's what we call them in academia. And as you can see from this image, you'll see it coming off of the sun. Whoops, right here, this big loop, right? This is off the limb here, and it's curled because of the magnetic field that jails the plasma. This is plasma, of course, is gas that is electrified. It's charged. And so it actually will follow the magnetic field. It sees the magnetic field. The magnetic field will jail it. And as this thing then goes in this image, this is the coronagraph image, you can actually see it expanding outward, and hopefully you can still see it. Hopefully it's not too dim of a loop here. And I think I showed this last time as well, that that loop, that magnetic field continues to jail this thing even as it moves out of just off of the sun's disk and into the solar atmosphere, and even beyond the solar atmosphere out into the solar wind. You're looking here at 15 sun lengths away from the sun. The sun is just this little tiny orange circle in the middle on this side of the image right here. And you can see already so close to still so close to the sun. Look how large this structure has already gotten. So by the time it reaches Earth, believe it or not, this structure, this coronal mass ejection, this massive belch, for lack of a better phrase, of stuff is actually as wide as a quarter of the distance from the sun to the Earth. So that's how big these structures can get. Can you imagine that? It's a quarter of an AU, meaning the astronomical distance between the sun and the Earth. Take a quarter of that, and that's how wide these structures are by the time they hit Earth. So these are massive structures, and so they envelop the Earth completely and take about a day to blow over the Earth entirely. And so they cause what are called geomagnetic storms, which is where you get aurora, you can get auroral propagation, you get the magic band lights up, even 10 meters lights up. On the night side, propagation is very different than on the day side, because on the night side is where all of that stuff, the interaction with the Earth's magnetic shield occurs. And you get all the effects from it. And it's a very complicated ballet, and it couples down into the ionosphere. All sorts of fun things happen. But that is not, as you can tell just by this short description, that is not the same as what happens with a solar flare, right? Solar flare happens it's a day side phenomena. These, believe it or not, are more night side phenomena, even though they hit Earth head on. That's kind of in a nutshell how you can think about them. These also take days to reach Earth. So we do have a day, like about 4 days, well, anywhere between 2 and 4 days, typically, a warning that these structures are coming. And there's a lot more to it than that, but I'll stop there. Now, both of these phenomena can drive radiation storms, and that's what you're seeing here. This is a coronagraph image, just like, yeah, this one is. It's a coronagraph image, but this one has got a blizzard, as you can see. See this blizzard? Looks like a lot of snow, right? That is the energetic particles that come from these two phenomena. And I'll play it. This is a radiation storm, and this wreaks havoc for all sorts of things, including radio propagation. Of course, you don't see the radiation storm yet. What you're seeing is the solar wind and a bunch of transients. You're seeing a bunch of solar storms being launched. But here very shortly, you'll see the blizzard. You can't miss it. You'll see multiple blizzards. I'll let it play, so I won't stop it in the middle of one. So you'll see a couple. I think one of the big ones comes first. There it comes. It's ready, almost. And come on, fire. There you go. There's a blizzard. Then you'll see another one. There's another one. Oftentimes they do come multiples, one after the other after the other. You'll see probably another one if I continue to let it play. And they disrupt the ionosphere. Many of you probably know the DRAP model and the radiation storms. If you do know it, the DRAP model that talks about the absorption in the D layer of the ionosphere, the radiation storms cause both the high latitude redouts that you see here. And they're polar. They happened high latitudes, day side, night side, it doesn't matter. So as you can see very, very quickly, if you have solar storms and solar flares, you get both the day side and the night side covered, and then you get the poles covered with radiation storms. A lot of times all these things happen at once. So pretty much you can trash the Earth in terms of radio propagation very, very quickly when you get some very inclement space weather. And then the last thing is, like on the right side, yeah, the last thing is coronal holes. This is where fast solar wind comes from. And fast solar wind can oftentimes mimic what a solar storm does. So these two are very similar. It's just that fast solar wind is a bit different in the sense that it recurs every 27 days during certain parts of our cycle. And that's actually a bigger issue for satellite operators, because it energizes our radiation belts, and not a huge issue for radio propagation. It's actually kind of nice because we can actually predict when these structures are going to rotate back into view and cause more havoc for us. So this is probably the most easily predicted effect at Earth, rather than the others, which are a bit harder to predict. But anyway, at some point, if you guys ever want me to go into these phenomena, I will go into them in great detail. And so you can all be space weather experts and stare at the sun and know exactly whoops, that's interesting, know exactly how to do a forecast actually. So last time, let's talk about the solar dynamo. Last time, hopefully some of you remember this. The solar dynamo is what causes space weather, right? It's really just the tick-tock, tick-tock of our star. There's two main effects, and I'll go over them reasonably briefly. This is all having to do with magnetic field. And again, I hope you, if you need, I think the last time I did the Papa Talk, if you didn't happen to see it, I'm not sure we recorded it. David, can you nod or shake your head if we recorded it or not? I forget. Do you remember?
Yes, we did.
We did record it. Okay, good. So you can go and review it and catch up on some of the stuff. If it seems like I'm going over this really quickly, and I am, so you know, my apologies in advance if this stuff seems like I'm not covering it very well. I'm just trying to get your minds, you know, refreshed. This was all about magnetic fields. So you can see the poloidal field lines. These are field lines that go from north to south. These are magnetic field lines like guitar strings. And the thing with the sun is that it's not a rigid rotator. It has differential rotation, meaning that because it's a ball of, you know, plasma, it's a ball of like liquid and gas. It's not like a rock. So different parts of it can rotate at different speeds. And sure enough, it does. At the equator, it rotates a little bit faster than it does at the poles. And because the way the magnetic field is jailed in the plasma, it's what we call frozen in flux. And again, I talked much more about that last time. Excuse me, the magnetic fields, then the guitar strings are getting stretched. They begin to get stretched more at the equator because they're being pulled by the rotation of this plasma faster, you know, this electrified gas, faster at the equator than at the poles. So they begin to be stretched that way. And magnetic field lines don't care if they're stretched. They don't like being bent, but they don't mind being stretched. So you can stretch them into this configuration quite easily, right? By just continuing to stretch them. Again, they don't mind being stretched. They don't like being bent. So there's a lot of forces at the equator from the bent stuff, but all these straight lines going, you know, this way in the northern hemisphere and this way in the southern hemisphere, that's okay. They don't mind that. So this process is called the omega effect. Okay, and it's one of the parts of how the dynamo works. You start out with straight lines going, you know, north-south, and you end up with lines going east-west, meaning, you know, sideways, right? Horizontally, vertically to horizontally. But in doing so, in doing the omega effect, you also get these field lines twisting. They like to roll over. And if anyone's ever taken a rubber band and you've twisted it up, before too long, as you continue to twist it, you take it straight out and you twist, 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 twist. Before too long, that rubber band kinks, right? It gets these little kinks in it. Well, that is really what we're talking about in what we call the alpha effect. Okay, and when you get these kinks, as you twist, twist, twist these field lines, the kinks pop out of the surface of the sun. You know, they float to the surface. They're actually very buoyant. And so they'll poke out of the surface, and I talk about those as submarines, and I'll talk about that in a minute, but that's what causes the sunspots, okay? So the sunspots are a manifestation of all of this weird stuff going on under the surface of the water, as I call it. I use it as an analogy. You think of the submarines popping above the surface of the water and disappearing. And all of this stuff is taking place underneath the surface where you can't really see. But what ends up happening as you go through the alpha effect is that, again, magnetic field lines don't like being bent. So what they do is they try to reconfigure, and we call that reconnection, if anyone's interested. And when they reconfigure, what happens is that you get field lines that point in opposite directions, and they touch each other, and they reconnect, they change, they reconfigure. And instead of having these twisted loops like this, they'll actually break and rejoin themselves into a simpler configuration. So you get these vertical kind of loops like this that are kind of threaded by these horizontal loops. But notice these vertical loops now are reforming that field that goes north-south. And eventually, if you get enough of this done, you end up reforming the magnetic field in the vertical direction, in the north-south direction. But in this case, the field now points from south to north, as opposed from north to south. So in a nutshell, the basic process of the solar dynamo is this, okay? The omega effect plus the alpha effect. Okay, now it's a lot more complicated than that, but in a nutshell, that helps us understand how sunspots are formed. And I did show this this diagram last time, as we put the picture together. Anyone who remembers the butterfly diagram, and I apologize, the writing didn't, kind of got messed up there, don't know why. But I talked about the butterfly diagram, and we'll show it a bit more. What this is, and you can see from 1960 up to about 1990, where I kind of hide it behind the sun here. What you're seeing is a plot of latitude, 0 at the equator, and it goes up to 90 degrees in the north, and from the equator down to 90 degrees in the south. And what you're seeing are these things that look like butterfly wings, right? Hence butterfly diagram. They are the sunspots at a particular latitude, right? And they start, a cycle starts when, let me put my hands in the right place. Yeah, maybe over here. The sunspots start at high latitudes, and over time, they go down to lower latitudes until they get to the equator, and it essentially stops, and it starts all over again, right? And I talk about that as being, the sunspots are these submarines. They come up from the bottom of the water, and they poke to the surface, but at the beginning of the cycle, they start at really high latitudes, and then they submerge again, and then they come out again a little bit lower latitude, and they submerge again and come out even lower latitude. And over the course of time, they get to low latitudes, and that's how you can tell where you're close to the end of a cycle. It makes it nice because each cycle will have sunspots essentially at different latitudes. So the end of cycle, let's say 24, which is what we just passed, we had essentially all the sunspots that we were seeing over the past year or two have been really low latitudes, really like right, in this region here, next to the equator. But then, even as early as 2016, like December of 2016, we started seeing new sunspots that were super high. And we knew those were actually cycle 25 sunspots. They wouldn't be cycle 24 because 24 sunspots were at low latitudes. And there's another way, and I'll talk about that in a second. But that was one of the indications that we knew cycle 25 was starting, because if you could see, or not starting, but it was trying to gear up. And as you can see, even from this diagram, you can kind of see that the low latitude stuff and the high latitude stuff does overlap a little bit. As a matter of fact, sunspot cycles overlap by about 3 years-ish, give or take an ish, okay? Now what you're looking at, now let me stand on this side. So really, when you see this process that's happening over and over and over again, when you put it together in a picture of the sun, what you're looking at, hopefully you can tell what this is. This is the surface of the sun. This is what you would see in white light. As a matter of fact, you see a few sunspots here and there. There's a sunspot right here, as a matter of fact, that you can actually see with the threaded with red magnetic field lines that's kind of poking out. That's one of those loops we talked about. And as it pokes out, you can see it pokes out of the surface and then back in. But what you see in white light, because magnetic field lines are invisible, what you just see are the sunspots. We just see evidence of that submarine poking out of the water, right? But if you disappear down into the depths of things, and you can hopefully see the ghosty images of the magnetic field lines, you're seeing the whole omega effect, right? You're seeing those magnetic field lines being kind of pulled off, to the east-west direction, right? Being pulled this way. That's the omega effect. Of course, the alpha effect is creating these sunspots and popping them out of the surface of the water. And on top of that, you have this flow. You see these arrows? They show this flow, and in the northern hemisphere, the flow goes down and then back up. Sorry, my hands aren't quite in the right place. I'm trying. Down and back up, right? And then in the southern hemisphere, it does the opposite. In the southern hemisphere, it goes down that way and then back up. So at the surface of the sun, you've got flows, and these are plasma flows that move up on the surface toward the poles. But down deep, where those magnetic field lines really are, where they're all anchored, those flows are pushing down toward the equator. And believe it or not, that's what drives these magnetic field lines towards each other at the equator, okay? It's also what drives that butterfly diagram. It sure drives those sunspots down. So that's the interesting thing, is that it's actually the flows, what we call the meridional flows, that cause this, that cause the magnetic field lines constantly to be annihilated slowly but surely over the course of about 11 years. Okay, so that's kind of the picture. And I think I have, well, I'll show it soon. Hang on, let me just check. Where do I put that movie? Yeah, I'll show that movie in just a second. You'll see exactly what I'm talking about in a movie in about 4 slides. So hold that thought. Oh, why did you do that? Sorry. Okay, so hold the thought of this image, okay? Because you'll see a movie of it, and I'll play the movie multiple times and we can chat about it. Okay, so just kind of zooming in for a second, and I showed this plot last time, how magnetic loops make the sunspots look dark is basically you've got under that surface of the sun, we're looking at the sun from the side, those magnetic loops that pop out, right? If these are the submarines here, right? It looks like this is the submarine or multiple submarines popping out of the surface. The invisible part is this magnetic loop, right? But what happens is that below the surface, those magnetic loops block all this plasma. And all this plasma underneath, this what they call hot rising gas, it's not gas, it's electrified gas, so it's a plasma. This stuff is what brings the light up to the surface from the radiative zone of the sun. It actually brings the light up and out. But if you block that circulation and don't let that stuff come to the surface, it's kind of like blocking a pot of boiling water. You're blocking the bubbles from rising. You block those bubbles and it's going to appear dark. And that's exactly what happens in these things. So the magnetic field tubes, these are actually tubes, they block that light. And so that's why sunspots appear dark, especially in white light. And here's a better view of them. And again, this is something I went over before, right? Here is the direct submarine, okay? So if you've ever looked at an aerial view of a submarine from straight down, you'll see the submarine, right, looks very, very dark, right, as it pierces the surface. That's the umbra. Okay, so that's part of the submarine that's sticking above water. That's the magnetic tube that's poking out. But you also have the penumbra, right, which is the lighter, slightly lighter side. And what that really is if you still take that same image of the submarine, you look straight down. A lot of times if the water is clear, you can actually see the shadow of the part of the submarine that has not surfaced. You can see the shadow of it underneath the water, right? It's a little bit darker, so you can kind of see through it. You can't, it's not as dark as the submarine that's popped through the surface, but you see the hint of what the real, the huge shape of that thing is actually underneath the water. And that's kind of like what the penumbra is. And of course, this all around it, this is the pot of boiling water that's bringing up the light. So in here, the submarine, right, the sunspot is partly blocking that bubbling water and the light coming up. And here it's completely blocking it, okay? So that's really how you get it. And of course, sunspots can become, extremely complex, right? You can have just a little bit of these tubes popping up. You can have a whole armada of these submarines, which are all these different magnetic tubes. You can get a ton of stuff happening depending upon what the dynamics are going on underneath the water. But remember, it's all below the surface. So it's really hard to see all these processes occurring under the surface. And there's lots of things that cause these instabilities that then cause a lot of, really radically crazy and unstable sunspots to pop to the surface. Once you get a lot of stuff like this is what often causes the space weather that we see, right? If they're very magnetically unstable, you can end up getting, big coronal mass ejections, these big solar storms, big solar flares, and radiation storms as well. But that, again, is a totally different talk. Now, hopefully some of you are familiar with Hale's magnetic polarity law. If you aren't, here's a nice little, an easy way to remember. It's really about magnetic direction and magnetic polarity. So we're talking once again about about these submarines and now their magnetic polarity. And it's what's nice about the Hale's law is that it allows us to really see for the first time how the hemispheres differ, right? There's some symmetry between the hemispheres, but they're not exactly the same. And if you look at sunspots, this is a cycle near solar maximum in 1989. And you can almost immediately see, if I put my hand right in the middle, where there's no sunspots, I'll try to put my hand right there, you can actually see, I mean, there's a region, right, that is right around the equator that no sunspots are occurring. And this is because we were really, still reasonably early in the solar cycle. This is actually just a little bit before solar maximum. And so it's reasonably early in activity. And so the sunspots are still in the butterfly diagram, they're still at high latitudes, both in the north and the south. There's not a lot going on in the equator. So that tells you right away, oh, just by looking at the sun, you can say, oh, well, this is obviously reasonably early in the cycle because the sunspots aren't near the equator. Those meridional flows haven't pushed that magnetic field down to the equator yet. And so the sunspots are still pretty high. What else you can see right away is that if you look at the color code, okay, the color code is blue leading in the northern hemisphere, blue leading and yellow trailing. The colors just simply mean which magnetic field is pointing out and which magnetic field is pointing in. We have all sorts of ways of doing it. So this is, don't worry about the color code, it's relative, but it just means that they're pointing in opposite directions. But if you notice, everything in the northern hemisphere essentially has blue leading, meaning it's the first spot you see, and then yellow trailing. The sun rotates this way. So blue leading was going to be something that's on this side of the sunspot. Yellow will be on this side if there's a sunspot grouping, right? So blue will be the first one, yellow will be the second one that you see. If you ever forget that, just think of when the sun rises or when the sun rotates, when sunspots emerge on the edge of the disk on this side, what is the color you see first? That's going to be the leading spot, okay? So that typically, as you can see, are mostly blue leading and yellow trailing. In the Southern Hemisphere, exactly the opposite. Notice most of the spots, look at this one over here, for example. No, this one, yellow leading, blue trailing, right? Yellow comes first and then blue, right? And you see that all the way across. So you immediately see that the Northern and Southern hemispheres are opposites of each other, as they should be. The flow is opposite, the magnetic field direction is opposite, everything is opposite. If you look back at the alpha and omega effect, you'll see that. And yet, if you go to the very next solar cycle, look what happens. Okay, almost the same phase in the next cycle, because I can put my hand once again right across the equator. So we're still pretty high in the, early in the sunspot cycle. There's nothing happening at the equator. And yet look at the sunspot colors, the magnetic polarities. Now up here, yellow is leading, blue is trailing, right? That was what was happening down here in the previous cycle. In the Southern hemisphere, yellow is leading, blue is trailing. Next cycle, yellow is leading, blue is trailing in the Northern hemisphere. So they switch, which makes sense. I mean, the magnetic field flips, so you would expect to have the opposite happening in, that the polarities would switch in the hemispheres as well. So these, not just having the high latitude going to low latitude, but also having the polarity switch, those are the two fastest ways of being able to determine when you see a sunspot on the sun, which cycle does it belong to? Because if you know it's in the Northern hemisphere, and yet the cycle, the polarity of the sunspots for that cycle are a certain way. If something shows up at higher latitudes and it's got an opposite polarity, it likely belongs to a different cycle. So we use that a lot, right? And it's very useful when sunspot cycles overlap. And so if you go back to like 2016, all the way through almost the current day, you will see that we have had a lot of overlapping of the cycles. The nice thing though is that it also tells you when the sunspot cycles stop overlapping, right? If you've watched probably the last, 3 or 4 months, you just don't see any more cycle 24 sunspots anymore. They're just not any at the low latitudes, and they're not any with the old cycle polarity. So it's nice to know that we really are in cycle 25, despite the fact that the sun is still having these fits and starts. And it's also nice to know when you look back at Hale's law, which was created back in the early 1900s, that there were certain people in the physics community who were actually looking at the sun from a hemispheric point of view. And that becomes extremely important as we move to the future of space weather forecasting and solar dynamo forecasting. So let me show you that picture. We'll put it all together now so you can actually see that movie. Okay. And I can play it multiple times. Yes. Grant access. Why in the world are you telling me this? Yes, play, please. Okay, let me make this big. And I'll play it likely multiple times because we'll talk about it a little bit. So there's the sun, right? Hopefully I'm getting out of the way. There's the sun. You can see it in white light and it's rotating. So now we're cutting open the sun. And what you can see on this side are sunspots going up, and you're seeing the solar cycle. So once it gets to 100 and some odd, that's the maximum. It goes down to 0, that's the minimum. And inside, what you're looking at, of course, the gold lines are those magnetic field lines. And you watch them going from kind of being squeezed down as you look at the blue and red flows in this cut. So what this model is trying to show you is the meridional cut. So you can see the flows going at, if I can do it right, like this, out on the surface. And then as you get close to the deep part of the sun, you can watch those flows push, and they actually push down. They push down that magnetic field. And so the blue and the red are showing the flows and showing the different magnetic polarities associated with those flows. And the green and magenta are doing something very similar on the other side. But let me play it for you again. And you can watch how that works with the solar cycle. So you can literally see that it's essentially the alpha and omega effects, at least in the deep sun, that are driving the magnetic field that driving the forcing of it down, the magnetic fields to get crushed and crushed and crushed and crushed, forcing the sunspots that pop out. They become what we see as the butterfly diagram as we watch these things go from starting from high latitudes and squeezing down to low latitudes. And the process just repeats over and over and over, with each new polarity being slowly pushed from high latitude down to the equator, where it slowly annihilates. And then the process begins again at the high latitudes with the new one. I don't know if any of you have ever seen that particular model before, but that's pretty much how it works in a nutshell. Okay. And I'll definitely take, I won't take questions right now. I'll wait till we get there. I want to take questions right now, but I know I have a limited time. So I easily will come back to this if we need to. Okay. Okay. So.
Tamitha, we could take questions actually.
Oh, okay. Does anyone?
Yeah. So let me
have a question?
Let me just mention before we take some questions. Let me just mention that we're trying to finish up our door prizes. So if you have a wish, we're gonna extend the door prize window for another 10 minutes or so, and then we're gonna close it. So now's a good time to go to the Papa System website and purchase some of those door prize tickets. You can see the prizes that are offered. And this is a way for the members to really support the Papa System. Going forward in the coming year, we have a lot of projects that we want to accomplish in beefing up the hardware at the hilltops with generator power and so on. So it's very important that that we help the Papa System not only with our membership but also with our donations and door prize tickets. So consider it this way: what would you pay to go to the movies? You know, if you wanted to go take your significant other to the movies today, if you could, what would that cost you? Well, this is way better than any movie I've ever seen. So, you know, that's the way I consider it. So, and you have a chance of winning some really great prizes. So I encourage you to go to the Papa System website and purchase some door prizes if you haven't done so already. And we'll shut that off in 10 minutes. So, Rex, any update on that?
Yeah, we've sold a couple batches of tickets in the last 10 minutes, say. So,
okay. So is it okay to extend it 10 more minutes?
Yeah, I'll need about 15 minutes to get the tickets already between the time we turn it off and the time we draw. But yeah,
she probably has another little while. So let's do that. Let's shut the tickets off in 10 minutes so everyone has an opportunity that's here that hasn't purchased any door prize tickets. And then we'll continue with the talk. Actually, some questions. I think she wanted to field some questions. So let me go to gallery view here. Anyone with a question for Tamitha? You can unmute if you want to ask a question.
Yeah, I got one for Tamitha.
Yeah, go ahead.
Yeah, the part of this the space science, you know, on the International Space Station, is that part of it about the radiation? You know, how much radiation they're absorbing throughout their, you know, while they're up there? Is that part of the research they're doing up there?
Yes, partly. Sadly, with the space station, you know, because they're in low Earth orbit, they don't get nearly the amount of cosmic ray penetration and solar energetic particle, the radiation storm radiation that we would get at let's say at higher orbits or even interplanetary, and so it limits some of the work that they do, but also, you know, I mean, that's the whole reason why, for instance, the SRAG has been created. Which is the Space Radiation Analysis Group down in Johnson, is to keep those astronauts safe, because they've got to dive under water storage and bunkers in the space station to deal with that. There is a lot of testing going on there, but they also have to deal with, you know, anytime they do EVA, they've got issues with worrying about radiation. And then also, because they're in low Earth orbit, they actually have an additional kind of radiation that they have to worry about from something called SAPs, which are they're precipitation events, and they are, I think it's called SAP. I'm thinking maybe I got the wrong acronym, but what they are these are precipitation events of radiation from the radiation belts, believe it or not. And they actually precipitate at auroral latitudes, and they actually can cause extremely high doses of radiation for any astronaut that happened to be out on an EVA. The sad thing is that they don't happen when we have radiation storms at Earth. What they happen during geomagnetic storms. So when a big CME hits Earth. And it's a totally different phenomena, and sadly, not a lot of analysis has been done in that regime yet. The astronauts are wearing dosimeters, but oftentimes the dosimeters are in different places, or they're only on one part of their EVA suit, and sometimes they get shielded by other parts of the body. So it's like the wild, wild west. We are doing tests, we are learning more, but it's still a very, very massive frontier, and we don't really pretend to understand it all yet. And so, it's a very active field of study. I wish we could predict radiation storms. That would help us immensely, but we aren't even there yet, even in the pristine solar wind. So it's even tougher inside the Earth system, which is so complex. So hopefully that answers a little bit of your question, but I know it's not a fulfilling answer.
I had a question for you, Bernard, KG6FBM. Being that we rotate around the sun, does it create, or does it appear that the solar spots are moving faster, like on the top, and slower on the bottom?
No, it doesn't, but it does change how we see the actual solar rotation. We are co-rotating with the sun. So basically all the planets all rotate the same direction. We're all rotating, including the sun, as it does its axial rotation. So we are chasing the sun in a sense in its own rotation. If we were to be completely halted, and had what we call an inertial reference frame, the sun actually rotates in about 24 days, at least at the equator. At the poles, it's longer. It's about 28 to 30, depending on who you ask, and what latitude you're at. There's actually a lot of studies that have been done on that. So, the sun itself is rotating at a different rate depending upon what latitude you're looking at on the sun. But yes, we chase the sun in its orbit, which actually lengthens its orbit for us. And that does have an effect on everything, not just the sunspot, not really the sunspot's speed per se, other than just the rotation of the sun, but it does affect how we perceive the solar wind. And the Parker Solar Probe right now, which is actually catching up to the sun and being able to measure the solar wind from the sun in a single location, co-located with a certain part of the sun. So it looks like the sun's rotation stops to Parker Solar Probe. We're discovering all sorts of things about the solar wind we had no idea existed, because we've always been locked in this, in this 27-day rotation reference frame. So hopefully over the next decade, we're going to be learning a lot more about how the sun works and how it emits solar wind than we've ever known. So hopefully that at least addresses partly your question.
I have a three-part question, KM6ABH.
Okay.
It's back to the space station. You just brought up something that I kind of knew about but wasn't aware, and the radiation effects on the station. Because even at this point, we're hearing some warnings for pilots, who are constantly in the plane. The first question is, do they get a heads up? And then you mentioned that's first part of a storm coming. And the second part is you mentioned something about them going undercover or into some kind of environment that protects them. And so the second part is, what is that environment? Is that like a lead shielded compartment? And then the third part of the question is, has there been any examples or known cases of any type of radiation poisoning? Nobody's died from it, obviously, but any kind of mild effects that they've experienced?
Okay, so the first part, asking, do they get a warning when these storms occur? Yes, they get a lot of warnings. The only time they don't get a warning is when we have things like stealth CMEs. These are solar storms that are not observed launching off the sun because they are very slow. And this is an area that I'm actively working in to try to better our predictions, because they actually cause, when they hit Earth, when you have they'll cause a geomagnetic storm. So you have this big storm response, and it becomes a real issue for astronauts for other reasons, not just the radiation that from these auroral events, but also from a point of view of charging. The spacecraft, I mean, the space is hazardous, and everything out there is charged. And when you have something as large as the ISS and the solar panels of the ISS being football fields in length, it's you know, the potential drop, the potential difference, or the charging potential on that something that massive ends up being huge, because it's integrated. It's an integrated effect. So you don't have to charge something very much, but because it's so large, it scales, right? Because it's an integrated effect. The sad thing is that the spacecraft, I mean, that the ISS, the surface of the ISS actually charges in one direction. Let's say positively, just for sake, I don't know which it is, but it charges in one direction. The EVA suit of an astronaut charges the opposite polarity. So it causes very often discharges. And that right now, I think, ends up being one of the biggest risk factors they have. And I've been contacted multiple times about this. But they have risk factors there because not just getting radiation dose, but actually getting shocked, which is what ends up happening, because you get these discharges. You get shocked badly enough and it can cause numbness. They've had astronauts come in from the ISS with numb hands and numb limbs. You know, obviously it could stop your heart if the charge goes through your body in the wrong way. It can cause people to aspirate or choke, or even, you know, sorry to say, vomit in their spacesuit. So, you know, and these things become life-threatening situations very, very quickly if you're locked in a spacesuit. So those are some of the biggest risks that they have right now, because they're completely uncharacterized. So, you know, that's probably one of the biggest things. And then the SAP, the high dose radiation, short burst, high dose radiation effects are things that are only beginning to be, you know, calculated and quantified. So have there been issues of radiation sickness before? Yes, there have, but have they been correlated with space weather? It's hard to say, because we haven't had necessarily the right equipment, you know, or the right awareness. You know, all these things are things that we're still learning. And so it's very difficult to have anything but anecdotal evidence of these types of you know, of events. And so there's a lot of forensics analysis being done saying, ooh, this could have been the cause of this. But, you know, it's, once again, it's more like a smoking gun. And that's just the state of the art. We're even at that state of the art when it comes to spacecraft, because we have a lot of that stuff happening with spacecraft, where we do believe it was a space weather event that you know, fried something and took something out, because it happens during a space weather event, a radiation storm or whatever. But again, it's very difficult to have these situations where it's absolutely fundamentally true. We know that it's the space weather that took it out. We do have those events, but not typically with humans. We have them far more with spacecraft. But we're getting there. We're understanding that this is a field of work that needs to really raise its bar when it comes to human safety, especially as now we're having civilian astronauts, and we're now going to start trying to fly, you know, have flybys of people at Mars. It's getting to be pretty serious. But there's you know, there's a long way to go, and I could talk forever on this, but maybe we could talk offline about it. And then the last part, the other question, yes, what the astronauts dive under, and here's yet another part of the complication of radiation poisoning. The astronauts dive under water storage, and the reason why they use water is because water can stop not just the particle penetration, but it doesn't emit bremsstrahlung radiation. If you have things like heavy metals, very dense materials that you are trying to shield, these primary particles, these very, very energetic particles, yeah, you can stop the primary particle, but the problem is you create a secondary, a daughter product. You basically create a cosmic ray shower, or in this case, it's not cosmic rays, it may just simply be a solar energetic particle, but you create a shower of secondary products like bremsstrahlung, so X-ray, You can do X-rays, you get pions, muons, all sorts of things that then actually end up creating a worse radiation dose environment than just letting the primary particle go through you. And that's a function of how thick the shielding is. So honestly, having thick metal shields is really the wrong solution for astronauts, and they need something else. And that is becoming a very big hindrance for the Artemis mission, for the Gateway, for missions to Mars. That's why they keep talking about having water storage, is because water can actually prevent Stirlung from creating a worse environment. It's like almost when you have these things, you actually end up putting astronauts almost in a microwave and cooking them. So it's almost better that they stand out on the surface and just take the full dose of the primary particles, because in the end, they end up having a lower dose of radiation that way. So that's another thing that complicates trying to quantify this stuff, if that makes any sense.
Yeah, thank you, Tamitha. I think you should go back to your presentation now.
Yeah, I know I'm getting off.
And then do questions more at the end. Thank you.
I will do. Yeah, sorry about that. Okay. So the interesting thing that we've learned, about the solar dynamo is that, there's these basic processes, and we can understand that. But what we are also beginning to learn, and it's hard because the sun doesn't allow us to probe it very well, especially through the radiative zone. It lets us probe the convective zone, but not the radiative zone. It's really opaque to us. So it's really, really difficult for us to understand it. But by looking at other gas giants in our solar system, like Jupiter and Saturn, for example, we are beginning to understand a bit more about how these differential, rotators, just the act of spinning on their axes, how they create different processes, different flows inside the actual, inside their interiors. Well, within their interiors. And so what we've begun to realize is that there are different, in a sense, dynamos that are occurring at different length scales and different depths within the sun itself. And as you can see here in this pink diagram, you can actually see the convective zone. We have a certain amount of the certain process that we've seen. We've got those big tubes that come down. Remember talking about the big processes that cause the flows to move toward the equator down low at the bottom of the convection zone, but then come up to the equator, and then at the surface, they move poleward. And what we've learned is that we actually have even a smaller section right at the surface that, as you can see here, these little teeny tiny curls that do right at the surface of the sun that don't even go very deeply into the convective zone. So if you have magnetic fields and stuff that are sitting more on the surface of the sun, or much weaker magnetic fields, they're going to be controlled much more by the stuff that's happening on the surface, as opposed to the stuff that can reach much deeper all the way down to the base of the convective zone. And sure enough, as we've done models of this stuff, we begin to realize that here's just examples of some of the patterns of the convections that you can see. Here's a cut through the convective zone. It's kind of a meridional cut. And so you just see this area. And if you look here where you see the deep red, right, that's down at the base of the convection zone. And if you take a cut through there, this is what you see on that plane. Okay, our big convection cells, really deep, large scale, macro scale things. If you go a little bit higher, as you can see here in this second panel, you can see that red, right? It's a little bit higher. It's not quite as deep as what you see in the top one, but it's kind of in the middle. And sure enough, as you take a look at what type of convection patterns you see, look at that. It's a little bit tighter, right? A little bit smaller scale. The bubbles are getting smaller. And if you go just to the very surface, which is this bottom one here, if I'm pointing in the right place, you can see where the red is. It's just right at the surface. Look how tightly and densely packed those all the convection cells are. Okay, so we're seeing multiple dynamos, and this is work that's just kind of still continuing to churn, for lack of a better phrase, no pun intended. And when we start looking at the sun, not just from the scale of just a single sun and having symmetric hemispheres, but also from the different depths of these different convection patterns, depending upon how large something is, it begins to start helping us put a picture together of why we have different size sunspots, as well as where they are in the solar cycle, what latitudes they're at, how they drive down to the equator, and when we would expect to see them. And so, as you can see, just from this is just over the course of like a year. These are all sunspots that have been picked out. You can see all the different sizes, and you can see Hale's law in effect, which is the polarity. The stuff in the southern hemisphere has black leading, white trailing. The stuff in the northern hemisphere, for the most part, has black, do I say that right? It has white leading, black trailing. And so they're the opposite. But then you also see that there's a tilt to these sunspots. You can see that with the colored circles. Some of them tilt this way, some of them tilt that way. Usually the smaller ones don't follow what's also called Joy's law. We see a lot more violations with a lot of the small sunspots than we see with the big ones. And a lot of that is because these small sunspots are following the beat of their own drum, so to speak. They're following the beat of dynamos on the surface scales. And that is beginning, those types of things we're beginning to really dig into in terms of understanding the specifics of how the dynamo varies, okay? Because it's not just a light switch, right? It's not every 11 years the solar magnetic field flips and then we start again, and every 11 years, pop, 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 pop. There's some sloshing, right? Some cycles are large, some cycles are small. And we're trying to get a better idea of how that happens. So here's an example of butterfly diagram showing those long-term trends, showing how dynamic the sun really is. And this cycle goes, this is from cycle 12 all the way to cycle 24 in 2020. You can see the top panel is the butterfly diagram, and it's done sine latitude. So instead of going from 0 to 90 degrees, it goes from 0 to 1. It's just taking the sine of the latitude. Sine goes from 0 to 1 and you know, in a sense, back again. And then down at the southern hemisphere, it does the same thing from 0 to 1, but it's still the same thing. It's still 90 degrees essentially down here. So you can see each cycle may be a little bit, you know, different, right? Maybe a little bit longer, maybe a little bit taller, right? Higher latitudes. Notice that some of the biggest cycles, like you can see here, this is cycle 19, right? Notice that cycle that the sunspots actually look like they started at a slightly higher latitude. There's another hint. If you have sunspots that start at really high latitudes, oftentimes the cycle is bigger, right? It's got more sunspots and not just more sunspots, but larger sunspots as well. And if you really start looking at, in this case, the bottom one is a sunspot area, how much of the sun was covered during that particular solar cycle, you can start seeing some long-term trends, right? And in fact, up to cycle 19, you saw this rising of each cycle got a little bit larger than the previous one. This is what we call a grand solar maximum. Notice outside of our little outlier in cycle 20, everything since then has been kind of trending down, okay? Well, for those of you who've heard of it, this is the grand solar minimum. Sadly, about 10, 15 years ago, we had some very overzealous scientists saying, oh, we're gonna go into another Maunder minimum, sunspots are gonna disappear. Look, 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 it's just gonna go down and, you know, past zero, right? We're gonna, you know, the sun is gonna shut off and it's gonna be done. No, this is just simply a modulation over time. And it's a modulation of our solar dynamo. And really what happens during this is it really modulates the strength of the solar cycle. And so when you have a strong solar cycle, you're going to have a lot more of those magnetic sunspots, you know, those magnetic field lines popping through the surface, creating more sunspots. And that's simply because the magnetic field is stronger and it becomes more buoyant. So it's much easier for the submarines to pop through the surface. During a grand solar maximum, as the magnetic field weakens in the sun, that doesn't mean the dynamo goes away. It just means less of those magnetic field lines, because they're weaker, they're not as magnetically buoyant. The submarines have a harder time poking through the surface. And in the case of the Maunder minimum, the submarines couldn't pop through the surface. Doesn't mean the dynamo goes away. It just means it all happens underwater. We don't see it, okay? But it doesn't, so anybody who's heard about the grand solar maximum and that the sunspot and the solar dynamo is disappearing and it'll turn off and never happen again, that's not the case. We just, if it gets so bad, because of something I'll talk about in a minute, which is hemispheric asymmetry. If it gets so bad that the magnetic field weakens to a significant enough degree, then we don't have sunspots, right? True, but that doesn't mean the dynamo stops. The alpha and omega effect still occur. They just occur beneath the surface. Okay, but it doesn't look like we're gonna see that. We are actually even seeing evidence of cycle 26 already. So we're likely gonna be just fine. And if Macintosh and crew have their way, we actually might be done with the solar minimum, or the grand solar minimum. We may be back up, moving back up toward a more active sun. So what role does solar variability play? Well, we've already talked about it. The sun has a quasi 11-year periodicity as seen in the sunspot numbers. Here's from 1600 to 2000. This is a very popular diagram. I like it because it shows not just the Maunder minimum, but the fact that we had to use proxy measurements in red. This is before the modern age of the telescope. So we had to look at like ice cores and isotopes, cosmic ray evidence in ice cores, for us to kind of know where the sunspot activity, where the cycles were. But as you can see, this was a very deep minimum. Now it's not the only minimum that we've ever had. You can see we have a Dalton minimum in the 1800s, and we've had a few here. Here's the modern maximum, of course, as you can see, that we're beginning to come back down from. And all of this modulation of the 11-year solar cycle, which are the sharp lines that go up and down, up and down, up and down. But this average line that's showing this modulation, this is occurring because of other cycles that are competing, right? And typically longer year. In fact, the Gleisberg cycle is probably the largest. And the funny thing is that the Gleisberg cycle, along with some of these other cycles, actually occur on a much longer time frame, right? They occur 100 years and 200 years, stuff like that. And they actually affect the northern and southern hemispheres slightly differently. And therein lies the trouble. And I threw this in just for fun, just to let you know that when we look at the solar cycle, and again, I showed this on the other plot, you can see from solar minimum through maximum and then back down to solar minimum again. The activity levels aren't just seen in sunspots, right? We have a whole plethora of things that we can look at, including total solar irradiance, sunspot, and the sunspot number, of course, solar flare index. So in other words, how often do solar flares occur, as well as the radio flux at 10.7, the F10.7, which is, that's why we use sunspots as a proxy for all of that stuff. But every single one of these, as you overlay them on top of each other, really follow quite nicely. And we can actually look at filament eruptions. We can look at bright regions on the sun. We can look at all sorts of things that all point at what's going on with that solar dynamo. So don't think that the sunspots, the sunspots is the only proxy that we can use for solar activity. There are a lot of them, okay? And as you can see, again, with the heliosphere, I've got this here just for reference for you. I'm gonna stand completely out of the way because I've often been asked, can you tell me when was the first solar cycle and what do they all look like? Well, here they all are, right? Cycle 1 through cycle 24. We don't have cycle 25 really up there yet, but there they all are. And as you can see, up through about almost cycle 10, we really didn't even have complete month measurements. We've had to do proxies. We've only had something. We've maybe missing a few days here and there. So even in since telescopes, where we're actually looking at solar cycles and looking at sunspot number, we didn't have full coverage, right? Not everybody had a telescope staring at the sun 24/7. That only came later. And as you can see from all the variability, sunspots come in all shapes and sizes. Now, why do you think that variability is? Right? You can see some of these sunspot cycles have just a single peak and others have double peaks. And this is where I start getting into the idea of the tortoise and the hare, right? Sometimes you see one unified thing, but sometimes you see two, right? Two humps that are slightly lower, like this cycle that you can see, cycle 23. Now, if you start thinking about the sun, instead of being just a single body, a symmetric body, but rather think of it as two different hemispheres that sometimes are happy with one another and sometimes aren't. This concept makes a lot more sense. If I have two hemispheres of the sun and I look at them in terms of sunspot number, here's, let's say, the northern hemisphere, and then here's the southern hemisphere, and I look at sunspot number. Well, if I just look at the northern hemisphere and I see sunspots going from 0 all the way up to a maximum and then back down, right? That's a nice sunspot diagram, right? Looks like a nice cycle. If I do the same thing with the southern hemisphere, they start, they finish, right? And you got maximum, minimum, beginning, and end, right? Perfect. Now, because it's a superposition of things, if the two hemispheres are perfectly aligned, well, you add them, right? If you add them, they're going to go up just as high, right? It's going to double in height and be about the same width, right? So you'll have something that looks like this cycle, right? This single peak that's very tall. But what if the two hemispheres don't work in concert? What happens if they are very much out of phase, right? Well, now you've got something that starts, kind of drops a little, and then peaks again and then ends. So something that's twice as wide, right? And may actually have two maxima, two peaks. If, let's say, the southern hemisphere decides to peak before the north, or the north before the south, depending upon which way you want to look at it. Doesn't that look something like this, right? So suddenly something that was like complete mess, like, oh my gosh, why is there so much variability, simply becomes a matter of how do you superpose the two hemispheres? Do they maximize at the same time and minimize at the same time? Or are they completely out of phase with one another? Okay. Keep that in mind. Much of it can actually be that type of variability, that type of communication between the two hemispheres, behavior between the two hemispheres, can explain a lot of this. This is, I don't know if you guys know Velasco Herrera's paper, but this is just over a very large time scale using proxy measurements for most of it, from year 1000 all the way to the year 2000. You can see here's this is sunspot cycle. It's total solar flux or total solar radiance TSI measurements. And done with proxy, all in blue here at the top, up to about 1600. And then of course you see a lot more measurements moving on to the 2000s. That's because that's where we got into actually directly observing the sun. We didn't have to use so many proxies. The middle panel, so you see the Schwab cycle, the 11-year cycle going up, down, up, down, up, down, all through here. The middle panel is where they try to take all the models that they've used to try to get the low frequency variations of this. So the modulation of that 11-year cycle. That's all the models they used. And then down at the bottom panel is where they normalized all these models to the same baseline. So all of the lines now are scaled so that they overlap one another essentially on the same scale. And you start seeing some nice alignments, like the Oort minimum, okay, the Wolf minimum, the Sporer minimum. Here's the Maunder minimum. See it here? This is the one we had where the sunspots went away. There's the Dalton minimum, the Modern minimum, and now the grand maximum that you see here. Okay, so if you look over time scales of ages, right, thousands of years, or 1,000 years at least, you see the sun has gone through many, many minima, some deeper, like the late medieval minimum was much deeper, and the Wolf minimum was much deeper than the Maunder. The Maunder isn't even as quiet as the sun can get, right? And so, yes, we are in another grand minimum. If we call the big peaks the grand maxima and the other ones, the troughs, the grand minima, we are in another, we're going down into a grand minimum. Okay, we don't think it's going to be nearly as deep as the Maunder, but this is very common for the sun. And as a matter of fact, when we pull out all the frequencies, I mean, all of you are likely very savvy when it comes to this. You guys know how to superpose frequencies and Fourier analysis and all that. So here's the Schwab cycle, the 11-year cycle, and here's two different frequencies. This one is the 120-year component, and this is a 240-year component. And as you pull them out, look at this, right about 1600, about 1650, if I can get my hand in the right place, right here. Both the 120-year component and the 240-year component had troughs. And look what happened. This is where we had the Maunder, right? Because I have this on the same scale as the plot beneath. I stretched it out to make sure that they lit up. And sure enough, that's where the Maunder minimum was. Now, granted, there are other cycles that compete that I don't have. Here's the Maunder. There are other cycles that compete with these two. This was just an example from her paper. But as you can see, if I go straight up, that's where the Maunder minimum happened. So you really do get these, modulations over time. And it really has a lot to do with how do these other cycles affect the northern and the southern hemispheres. So where are we now? Well, the recent cycles have been showing the dramatic changes, and this is really the end. It was actually the end of cycle 23 that got us to kind of start looking at, okay, where are holes in understanding the dynamo? Because it's obviously not just a light bulb. And that started to make predictions more complicated. And if I recall, I probably showed this plot to you. I'm not going to go into the depths of all of this because we had it last time. But we are knowing that these cycles, when we get to these lower cycles, in these more complicated cycles, they slow down, right? They're longer. Remember how we talked about, you know, the hemispheres, if they're not talking, not in concert, they don't agree with one another, you're going to have a longer cycle than if you had them agree with one another. And we'll go into that. And that's exactly what started happening when we were trying to get to that, the next cycle, the predicting cycle 24. At the end of cycle 23, we had a mess trying to predict what cycle 24 was going to be. There were multiple predictions in 2008, 2009, and in 2011, and we kept having to shrink the cycle size and push this maximum out. So we had first thought it was going to be 2012, and it was going to be about 150 sunspots. Ended up with that, the minimum just kept on going. And in 2013, we made another prediction and shrank it. I mean, in 2009, we made another prediction that the maximum would happen in 2013, and we made it a smaller cycle. Then in April 2011, we had to make yet another guess. And we thought the maximum would be in 2013 and a half, and it would be a really small cycle. What ended up happening was a double peak cycle that was actually higher than our previous prediction, but it actually peaked later. So we were completely off. I mean, nothing was right. And as we're learning, these are because of the hemispheric asymmetry, and it's causing these double peaks. Instead of having a single peak and a short cycle, we're having these longer cycles that are double peaked, right? And you can imagine if you're going to have a double peak in a cycle, well, doesn't that also mean that when you get down to solar minimum, you're going to have a double trough for solar minimum, right? I mean, doesn't it make sense? If the two hemispheres decide, like, let's say the north wants to go to solar maximum first and the south wants to go to solar maximum later, then if the north gets down to solar minimum, it goes through solar minimum, and then the south maybe follows. And so you'll have two troughs, just as you would two peaks. And doesn't that extend the solar minimum out longer? Yeah, it does, actually. So everybody, I'm sure, remembers SWPSE's original prediction, which basically showed you that they could punt pretty well, because they took what solar cycle 24 was, they blurred it out, and they pasted it here for solar cycle 25. I had a big laugh at that when I first saw it, that this was as good as we could do in terms of the consensus. Since then, they've revised their prediction. And to this day, they think that solar cycle 25 is going to peak in 2025 and have a sunspot number of 115. I think that's still their full consensus. But again, this consensus is based on a single sun that has both hemispheres that are symmetric, right? They're not against one another. So let's talk about a different prediction, and we'll talk about multiple ones, but let's talk about this prediction. I have for a while now, probably 5 years, been following McIntosh et al. And the work that's been done at NCAR and UCAR very seriously, because they actually are looking at the sun just as you would look at terrestrial weather. They're seeing Rossby waves on the sun, just like we see here at Earth. They're looking at the flows and seeing very common flows that we see in our own atmosphere and in the atmospheres of other gas giants. And because we're able to look at these and know a lot more, especially through terrestrial weather, we're able to understand these flows and understand the dynamics in our terrestrial atmosphere, because we've studied them for so much longer. We can take certain things that we see on our star, for example, and apply some of the terrestrial tools, some of the meteorological tools that we've used. And that's the neat thing about NCAR and UCAR, is that it's probably the only place where solar physicists and terrestrial meteorologists work literally across the hall from one another. Nowhere else in academia do you find that, but there. And I believe that's one of the reasons, or the main reason, why they are ahead when it comes to looking at the sun, and not just looking at the sun as a single entity, but rather looking at the sun as a system, and looking at each hemisphere as having its own unique processes that are dominating its behavior. And so if you look at McIntosh et al. In 2020, they have a prediction that has raised a lot of eyebrows, especially in the amateur radio community. Some of you might have even seen Scott speak on this. His prediction, or their team's prediction, is that there's a very good chance that sunspot 20 or cycle 25 will have a sunspot maximum that's easily over 200. In some instances, maybe as high as 250. And its peak will likely be in 2023, give or take an ish. okay? Which of course goes totally against the downward trend that everybody sees from this grand solar minimum. Most people believe cycle 25 will look like cycle 24, maybe a little bit higher, maybe a little bit lower, but nothing like this that bucks the trend, right? So I have to say, poor Scott, he's definitely a rogue, and he's gotten more than his fair share of grief from the solar physics community, because as you can see, it just doesn't look like, you know, this kind of cycle could possibly be real, because the last cycle we had that would have exceeded it is cycle 19, which was a massive cycle. So this took a lot of guts, actually, to be honest, for him to publish, and I'm glad he did. And his model, he actually has two predictions in Macintosh 2020. You can see, and this looks like a little bit of a mess, but it's the same plot. But as you can see, there are two red lines in this. The first one is Macintosh with the most optimistic solar cycle maximum. And I think we've blown away from that a little bit, just because, and I'm only going to say a little bit, because of the respite the sun gave us at the very, very end of last year. We had a really good run in November, which I'll show you, but then it kind of died in December, and it's only beginning to come back up here in January. But so we may be slightly off of where this dashed line is, but boy, in November, we were really on pins and needles, because the sun was starting to wake up. And as you can actually see that data, he's actually got it in here. I think he does. Yeah, at the end of November, you can actually see there's a green spike. That's a monthly sunspot number, monthly sunspot number. It really spiked at the end of that year. And it was really close to the alignment of this very optimistic view that the sunspot maximum was going to be almost 250, like 230. And the peak was going to be easily by 2023. Now, of course, the other, and I should probably look here, the other predictions, the consensus prediction and also the mean solar cycle, which is this green line, just the mean solar cycle average since the 1700s, since 1750. You can see both of them are much lower, right? So the blue line is the consensus. The average is of all cycles is the green line, and then Macintosh, just even in the less optimistic, where he'd actually have a maxima in 2025, even that still has a very high sunspot number. So he's definitely deviated quite a bit. And here's the blow up of what I wanted to show you in, actually, let me stand on, well, no, I'm gonna stand on this side because I can see my preview screen over here. So this is just a blow up of the beginning of the cycle. Remember I told you that green spike? Yeah, that's this green spike going up. This was the activity that we saw near the end of 2020. And even the average number of sunspots was going up. So this is when we went, wow. And guess which hemisphere this was occurring in? The north or the south? Anybody take a guess? It's rhetorical. It was the south. It was the southern hemisphere, okay? Mainly because the southern hemisphere is leading. And I'll go over that, I think, in one of the next plots. But as you can see, this dashed line going up very, very quickly, that is really lining up very nicely with this early jump in activity in the southern hemisphere that we saw at the end of last year. Of course, his other prediction and the mean go up pretty much the same. Right here, that's the green and the red line here. But you can see the consensus, the SWPSE consensus of the solar physics community really goes up slowly. So what's nice about this when we zoom in here is that we'll be able to tell very, very quickly, probably by easily mid next year, maybe 6 months from now, we will be able to tell whether or not Macintosh and their crew is correct, or it's going to be one of these slow cycles like SWPSE predicts, because the cycles deviate very, very quickly from one another, you know, very, 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 very quickly. So over the next, we won't even have to wait a year. You know, a lot of people say, no, we have to wait a full year before we'll figure it out. I don't think so. I think we'll be able to see it in about 6 months. Now, this is the plot I showed last time, so I won't go over it too much, but I will remind you that in the top panel, we have what looks like a mess, but this is a sunspot plot. And in the black line, it's a little bit wavier than maybe you're used to because it's a monthly average. So it's got a little bit more trending stuff in there. But you can see the black line is the tall line. That is the whole sunspot number. But if you look underneath it, you can see blue and red lines, okay? The blue line is the northern hemisphere. No, sorry. The blue line is the southern hemisphere. The red line is the northern hemisphere. And if you see these vertical lines coming down, you're actually looking at, if you guys recall, I did go through this last time, but you're looking at, in the first case, you're looking in this line here, you're looking at the peak of the northern hemisphere. Okay, so the sunspot maximum for the north for cycle 23, okay, occurred first. In other words, northern hemisphere was winning the race to solar maximum. When you look at the second peak, which occurred over here, if you look at the blue line, that was where the maximum in the blue line occurred. That was the southern hemisphere. The southern hemisphere got to solar maximum last, right? It lost the race. And then of course we had then the trending down to solar minimum, okay? And this panel here is the butterfly diagram with the magnetic field. This is the butterfly diagram of bright spots on the sun. And I'm not gonna go over those this time, just because I went over those during the last talk. But you can imagine, as you see here, the blue, if you can look closely, you can see the blue line got to solar minimum last. The red line got to solar minimum first, okay? That is why we had such a long sunspot minimum, why the minimum lasted for so long. First, the northern hemisphere went to minimum, then the southern hemisphere followed. So just like we had a double peak in the maxima, we had a double trough in the minima. Now come up the rise of solar cycle 24, the solar cycle we just finished, right? Once again, yet another set of peaks, double peak. The peaks are actually further apart. Have you noticed? The two peaks actually look like they're slightly further apart than they were before. The hemispheres are even more out of sync than they were in cycle 23, hence a lower solar cycle number total, right? And if you look in this case, once again, the northern hemisphere, the red line peaks first, followed by the blue line, the southern hemisphere, okay? Here's where it gets interesting. And this is where the Aesop fable, the tortoise and the hare, becomes fun and is really applicable. The northern hemisphere is the hare, right? And we all know in that story, the hare thinks he's so fast. He's winning every race. He just constantly wins a race. He won the race in cycle 23. He's winning the race by a long shot in cycle 24, right? The southern hemisphere is the tortoise. It just keeps plodding along, right? But the hare gets so far ahead, just like it has in cycle 24, that it decides to take a nap. So as it peaks in the maxima in solar cycle 24, it decides to take a nap and it cruises. And if you notice, it's cruising, right? The tortoise then reaches solar maximum second, and the hare takes a nap under a tree. Look what happens right about, if I can see it on my thing, right about here. Does anybody see that? The red line, okay, because after you get to solar maximum, it was a race to solar maximum, now it's a race to solar minimum. But the hare has now fallen asleep under a tree. The tortoise keeps on going. So maybe the tortoise, the blue line, reached solar maximum last, but right about here, look how the tortoise decides to keep going to solar minimum. And the hare, the red line, just stays flat. See that? So at the end of solar cycle 24, as we chase down to and race to solar minimum, the tortoise beat the hare. The southern hemisphere went to solar minimum first. The northern hemisphere, it's still there, still sleeping under the tree. You want to know where we are right now? Wake up the hare. This is why we had in November, we had a sun that had bright regions all around the southern hemisphere. The southern hemisphere is ready to race back up to the maximum of solar cycle 25. It's ahead, it's going. It never slept, it never took a nap. The tortoise just keeps on moving. The hare is late now. The hare is sleeping. And as a matter of fact, as we, you know what, I'll skip this one for now. I'll go back to it. As we now begin to try to start racing back to solar maximum, I'm not even sure the northern hemisphere has learned yet that it needs to get through solar minimum and start going back up again. I think we're beginning to see that in January just over the past maybe couple, I don't know, days, maybe 3 or 4 days. But the fact that the Northern Hemisphere is so much lagging the Southern Hemisphere is really causing this solar minimum to kind of just have these fits and starts. The Southern Hemisphere multiple times, including in December of 2019, tried to start rising in the solar cycle 25. And then in December of 2020, or November of that year, it started trying really to rise. And I think eventually it's gonna, it's gonna pop, but it's going to go first. So it's ahead in the race. The hare is hopefully waking up slowly, but the hare is now behind us. So what we're going to see in this, probably in this cycle, is the Southern Hemisphere rising to solar maximum first and the Northern Hemisphere following it. The neat thing, and I did talk about this last time, is that once that Northern Hemisphere, once that hare finally does wake up and decide to go to solar, start working towards solar cycle 25, we will see the flux change very, very quickly. This is something called the terminators that we talked about a lot last time. Here's 2 examples. And again, I'm not going to go over this too much because we had it in the last talk. But here's the terminator for cycle 23. There's the terminator, that's the dash line for cycle 24. This is a sunspot number plot. And if you blow it up in this regime here, that's this plot here. The cycle 24, we blow up that region around the terminator, that's this plot here. And as you can see, we're looking at sunspot, radial flux 10.7 centimeter. You can see the solar flux was sitting at, right about 70. And as soon as we hit that terminator, geez, within just a few months, we had already jumped up past 100 and into 120 and on upward and onward. Same thing in solar cycle 24. We had a solar flux that was sitting around 70-ish. And then, it was almost like a light switch. So if we can get that Northern Hemisphere to wake up, we will be back. Remember, back in November, we had like 70 was the solar flux number, and it jumped up past 100, like to 105, and it's kind of gone back down, not quite so low, but it's gone back down. That's the kind of thing that we're trying to get. And it's interesting because it's almost like we passed that terminator, but not quite, because there's 2 different things. Yeah, I did that last time. There's 2 different things we're looking at with that terminator. One is solar flux jumping fast. The other is cosmic ray flux dropping. Okay, and I'm close to the end of the talk, so I'm going to show you the details of where we are. So yeah, I'll stand off to the side here. So this right here is the F10.7 flux that you see really close to the end of last year. Okay, October into November. This is where we started seeing that jump. I probably should have updated this so that you could actually get even a better view of it. The dashed lines are just the derived from solar flux from GPS measurements, but the measured stuff is the heavy solid line. And as you can see, we jumped very, very quickly at the end of October into November from low to mid 70s, clear up into 90s, and then we actually went up into the hundreds. And it went very, very quickly. Same thing with the X-ray flux. We had a couple actors on the Southern Hemisphere that literally pulled us, the X-ray floor, from the A, clear down at the A level, all the way up to almost a C floor, which is it's 2 orders of magnitude. So even in the X-ray flux, we saw this massive jump, and that was a big deal. But what we were looking for, and this is where we're confused right now, is that we're looking for the cosmic ray intensities to drop. As I talked about last time in the last class, cosmic rays peak at solar minimum because that's when our sun's magnetic shield is its weakest. So when it starts puffing out again and the solar flux rises, which is a signature of the magnetic field being stronger, that means it's also going to shield out more cosmic rays. So this is a plot from ULU, and I'll zoom in here in a second. You can see up and down, up and down, up and down. I believe this is the entire, since 1965. So you can see all of the solar cycles up and down, up and down, up and down. And you can see right here, and I plotted this just the other day, if I can get my hand in the right place. Right here, you can see the cosmic ray flux just beginning to trend down. And here it is here. This is now from 2019, essentially a year's worth of data. And you can see we actually peaked. The peak in the cosmic ray flux was pretty much right in here, which was about March or April of 2020. And you can start seeing that trend going down just slightly. You can actually see that trend in cosmic ray flux even better if we look at this, the Antarctica. I believe this is Antarctica, yeah, which shows the lowest energy cosmic ray flux. They get the highest fluxes at the poles. So you can see that trend actually going down even more sharply, okay? Now, granted, there was a little hiccup because there was over here, there's a little bit of a hiccup in the data. I think the data is okay. They had an experiment that interfered with it, but for the most part, I think the data is okay. And so you're seeing that trend. So I do believe if we're not at the terminator, we are unbelievably close, simply because we are now finally seeing the two things we need. We needed we needed both the solar flux index to go up, and we need the cosmic rays to drop. And we're seeing that. So, you know, Scott McIntosh and I are talking very specifically about it. And one of the things that he told me was, in the course of his work, and they're taking sunspots, you know, clear back to, you know, as early as they can. It's essentially 1750 when we started getting actual hemispheric data. We could actually really pull out, excuse me, pull out what hemisphere the sunspots were in. Prior to that, we really couldn't because it was a whole sun proxy. But once we started getting hemispheric data, what he did is he started looking at the time between each hemisphere, looking at that each hemisphere is essentially their own individual decoupled self. And they found that solar cycles do vary. The northern hemisphere has a particular distance between onset of each new cycle, and it's about 21.8 years-ish, give or take an ish. The southern hemisphere has a similar thing, but there's a bit more slop, believe it or not. So for some reason, the southern hemisphere seems to have a bit more variance in you know, the length of its cycle. And so when he plots this in terms of the current cycle, where should we be? This is his prediction, or that team's prediction of solar cycle 25. You can see again, the maximum is around 230 sunspots. But what you're looking at here is the error. This horizontal bar is the northern hemisphere. This is the error in the variability as the northern hemisphere goes to solar maximum. And sadly, the blue bar is the error in the southern hemisphere going to solar maximum. So the southern hemisphere actually could happen and go to maximum anytime during this period, okay? The northern hemisphere has a bit less variability, and you can see it by the red bar. It actually, you know, we actually have a pretty decent idea of when the southern or the northern hemisphere is going to go into solar maximum. So we know that it's going to happen by, according to his model, it should happen by 2023 and a half. That'll be the latest the northern hemisphere goes into solar maximum. The fact that the southern hemisphere is already leading the north, this is the reason, you know, means that likely the southern hemisphere is going to be at solar maximum before the northern hemisphere will. But since the northern hemisphere only has so much slop in all of the years that we've been doing this, or they've been doing this, means that the chances of the southern hemisphere and the north, you know, reaching solar maximum before the north, or by the time the northern hemisphere does, is really, really good. So that means we should have a solar maximum sometime in 2023. This is why he's so excited about what his model is telling us, is that if you look at each hemisphere individually, but then also look at the whole system as a whole, the model is saying that solar maximum really should be happening by 2023. And it's all up to whether or not that hare wakes up from that tree, from under that tree, and gets going. So within the next few months, if that northern hemisphere wakes up like we think, the chances of us having a solar maximum by 2023 in a very strong cycle is pretty good, okay? And I think, guys, that may be it. Let me see if I have any other slides. No, that's it. So here's I'll give you my final slide just for a moment. If you guys want to get in touch with me, I'll stand on this side, the same slide I showed, you know, during my last talk. There's all sorts of ways of getting in touch with me, and please feel free to do so. And thank you so much for your time. And I would love to answer as many questions as you want to throw at me.
Yeah, very good. Thank you so much, Tamitha. I do want to make a little plug for her Patreon that you can sign up for. She has a YouTube channel that's absolutely fabulous. And you can sign up as a Patreon and get previews of information that the regular public doesn't get. And for as little as $1 or $5 a month, you can join her community, which I did a year ago.
Thank
and
you.
it's really been wonderful to have that service. So she'll send out special videos and special emails and of events that are going on. So highly recommend that you go to her YouTube channel and take a look at all the stuff that she has posted there. It's really wonderful.
Good.
Okay, Tamitha. Any questions for Tamitha at this time? I had kind of one. It came up in the chat. What are the causes of the dysynchrony of the different hemispheres?
We believe right now, it has a lot to do with the Gleisberg cycle, which is the 60 to 80 year cycle. And it seems to be kind of sloshing around, as Scott puts it quite technically, sloshing around a mean. When it's not completely clear as of yet, and sadly, this is where my understanding of solar physics kind of falls off the map. I need to read a very classic paper from Hale, believe it or not, because Hale, way back in the early 1900s, really did a lot of this work regarding hemispheric asymmetry and looking at some of the other cycles. And the sad thing, you know, just like you find in so many other sciences, sometimes these landmark papers get lost in history and antiquity simply because people write them. They have these very brilliant notions of you know, and paradigm shifts in thinking. But because the field itself isn't ready for it, it kind of gets, you know, kind of pushed under the rug. I mean, you know, even Eugene Parker, when he first postulated the solar wind, the existence of the solar wind back in the 1950s, it took him more than a decade to get people to even pay attention to him. He was ridiculed for many years before people started realizing, yes, this is actually true. And I think the same is true for Hale. And so some of his papers are slowly being kind of unearthed and looked at from a slightly different perspective, with the understanding of terrestrial meteorology and how the hemispheres are working. But it is absolutely having to do with these pseudocycles that are modulating the overall 11-year Schwabe cycle. And so even though the Gleisberg cycle affects each hemisphere, you know, at the same time, apparently somehow it's affecting the southern hemisphere a little bit. I don't know if it's a little bit more, or if there's something else associated with it, simply because of where that southern hemisphere is magnetically related to even the celestial, the interstellar medium. We're beginning to understand the coupling of the magnetic coupling between the interstellar medium and our own heliosphere, our own sun. So there may have something to do with that as well. It's really hard to tell yet, but we do believe that the main part of it is the Gleisberg cycle. And some of the manifestations that we see, if you ever look at sunspots, if you ever notice, they come up in clusters on the sun. We believe that internal gravity waves and Rossby waves, which are all part and parcel of that dynamic, are very much part of this sloshing around a mean. So it's a very, very new field, and not too many people are talking about it yet. And we just are beginning to scratch the surface. So hopefully that helps answer that question as best I can.
Very interesting. Any other questions?
Oops, I've got one.
Yeah. Oh, okay.
Yeah, hold on, Mike. Go ahead, Bart.
Okay. Yeah, Tamitha, I've got a question that basically is from some of your other stuff, but I think it's important. The past couple months, you've been mentioning that the stereo satellite is getting out of sync with the sun a little more, and it's getting to the point where it's almost useless. Any couple of thoughts? Why is it getting out of sync? And secondly, do they have any plans to put up similar satellites so we'll have a good, hopefully, total picture of the sun, both sides of the sun?
Yes. Okay, hold on one sec. Let's see if I can, what I'm gonna do is I'm going to pull up where stereo is right now. And I hate that picture. Let's get this.
Pamela, could you explain what stereo is? I have a feeling some people don't even know what stereo is.
Sure. Sure. Let me switch my view here for you. So stereo is an imager that there were actually two of them. Oh, it's not switching. Hold on. There we go. Hopefully you see it now. Stereo is an imager. There was actually two of them. That was why it was called stereo. We had two spacecraft launched at Earth, and what the point of stereo was to have a stereoscopic view of the sun that was not Earth. If you're the sun and I'm the Earth, that wasn't along the Earth-Sun line. The stereo spacecraft were supposed to separate and kind of move around the sun, and that's again why we called it stereo. We had stereo A and stereo B, and they were launched in 2008 or 2009. I'm trying to remember. It's been a while. So they were launched quite a bit ago, about the same time. Actually, it might have been 2006, if I recall. They were a little bit earlier than when SDO was launched. And they get these gorgeous pictures of the sun, as you can see a couple of them behind me. And sadly, if you notice, I'll just throw this out right away. I'll stand on this side. No, I'll stand on this side. If you notice right away, you see this says stereo ahead. This one, which is this green sun right here, right? You see this center picture here. This is actually SDO. This is Earth view. And then you see, sadly, this no data for stereo behind. Okay, and I'll get to that in a second. Stereo behind is no longer with us. We only have stereo A, sadly. But the idea was, as you launch the spacecraft, if you put one slightly in a closer orbit to the sun than Earth, then it will move faster than the Earth moves. It will orbit the sun faster than the Earth moves. And it will slowly over time spread out and go advanced around the sun before Earth gets there. If you then take another spacecraft and put it slightly behind Earth, then it will be in a larger orbit, which then moves more slowly around the sun than Earth does. So it will then stretch out on the other side, moving slightly behind Earth. And over time, just simply having them in slightly different orbits away from Earth means that they will begin, from Earth's perspective, they will begin to do this. And they will slowly wrap around the sun on either side, meet in the back, and then come back out the other way. And sure enough, if they're launched in 2006, now it's 2021, that's exactly what's happened. So if I show you the plot, excuse me if I sneeze. I don't know why. Whoops, no, not that. Hold on. Where's stereo? There we go. And I don't like this image, so I'm going to go to a slightly simpler image. Okay. So here is stereo where we are today. And let's see if I can stand here. So I'm just about to sneeze. So excuse me, I'm not sick. I don't know why, but I just almost sneezed right there. So if I do, I apologize. So what you're looking at right now is an image looking down on the sun from the northern hemisphere into what we call the ecliptic plane. So it's like the flat Frisbee disk that all of the spacecraft orbit in. Here's Earth down here, okay? And as you can kind of see, it's in green, as you can kind of see, you see something here, it may be cut off a little bit, but this is stereo B right now, meaning behind. Funny, it seems advanced of Earth, but it's stereo B, and I'll tell you why it's here in a second. And on the other side is stereo A, okay? Now, it's not that this is the direction of advanced and that's the direction of behind. No, that's not it at all. Remember, the sun rotates in this direction. We go around the Earth, the Earth goes around the sun in this direction. So we're all rotating this way. And so is stereo A. When stereo A was launched in 2006, it was launched just inside Earth's orbit, and it took off this way. In 2015, it reached behind the sun. So in 2015, it was back here somewhere off the screen, okay? At that same time, stereo B, the blue one, was launched in 2006. It was launched, and it was slightly behind Earth, slightly larger orbit than Earth. So it trailed. And in 2015, it met stereo A on the far side of the sun. They both were up here. Let me pull my hands this way a little bit so you can pretend that this is as far out as the Earth orbit is. but they were both behind the sun in essentially 2015. We called it the conjunction. Sadly, stereo A made it out. I mean, excuse me, stereo, let me say it this way. This is stereo B going this way. This is stereo A going this way. Stereo A made it out just fine and started coming around the sun in this direction. And as we get to 2021, this is where stereo A is now, right here. Stereo B, on the other hand, it also continued its rotation, or its orbit around the sun. But in the conjunction period, one of its gyros failed, which meant it went into an uncontrolled spin, which meant it lost battery power because its solar panels were no longer connected to, pointed at the sun, which meant its hydrazine froze, which meant everything died. We tried for a few years to get stereo B as it began to rotate, pull away from the sun. We got contact with it at one point. We found out that its gyro failed. We found out its hydrazine was frozen. We tried to heat it up and lost contact with it again. We have not been able to get contact since. We think it's in a completely uncontrolled spin. And as it continues to come here, we are probably going to, as it gets really close to Earth here over the next 2 years, because it will pass this way, as will stereo A. I'm sorry if I'm blocking the image. Stereo A will also come this way. So we'll have stereo A and stereo B in 2024 pass each other, and stereo A will start going out this way again. Stereo B will start going out this way again, okay? But stereo B is likely, we're gonna try to get contact with it, but most likely we won't. So stereo A is our remaining solar far side monitor when it's on the sun's far side. But sadly, after its extended mission, it's only was supposed to get to the sun's far side. It's an extended mission now. So stereo A is now coming in through here. As stereo A continues to close the gap between Earth, between itself and Earth, it will reach Earth, essentially be the same view that we have with our solar or our instruments staring at the sun. It will reach this point at about 2024. Sadly, that's right at solar maximum when we need it on the sun's far side, but we're not going to have it. So that's why I complain about the fact that we're losing it. We will get it back because it will go this way and to start spreading away from the sun, get a different view than from of the sun than we have, right? Eventually, but that won't be until about 2027. So sadly, we're going to have a good 4-year span where it's going to be sitting kind of like, in this region and not giving us very much to go on in terms of space weather that we can't already see with our own instruments right here at Earth. So hopefully that answers that question. Did that help?
Yeah, very much so. I haven't seen that full explanation of the orbits before, but are there any plans to put up a new stereo B? And also, is there any way to put up satellites so that they'd be in geosynchronous orbit with the sun, so you'd be able to literally have stereo views of every side of the sun at one time on a continuous basis?
Understood. So there's no plans to replace stereo B. As a matter of fact, I think I'm not sure we're ever going to do a stereo mission quite the same way. However, obviously, I think we're going to continue to have funding for stereo A for however long it lasts, because we actually do use it for operations, which is even though it's an academic mission, this mission, SOHO and SDO have been invaluable to the operations, to space weather operations. So NOAA uses them all the time, even though they have always been academic in nature. But in terms of getting another sun, monitoring system that's not on the Earth-Sun line, which is this line here that goes straight right up to the sun, there is a plan. It's an ESA mission. It's an L5 mission. I forget the name of it. It's an L5 mission, but it probably won't be launched until about 2027. Now, L5, if you ask me what that is, there are these points called Lagrangian points, libration points. These are points at which the gravitational pull of the sun and some of the celestial bodies, in this case Earth, are such that it's a little bit of a stable point. And we have multiple stable points in and around the Sun-Earth system. L1 is probably the one you've heard of. That's where our upstream monitors are parked. It's about 400 Earth radius sunward. And we have multiple spacecrafts that orbit that point, almost as if it were like a planet of its own. It's kind of like having this mysterious, body. But it just happens to be that when you look at the gravitational forces, it's a stable point, and it means you use less fuel. If you're able to orbit that area, it takes less fuel to stay in that orbit. So we try to take advantage of these libration points anytime we can. So L1 is the most famous. We have L2, which is the one that is where some of the astronomical telescopes are also parked. Because they're constantly in shadow of the Earth, or Earth's shadow, so that they don't get the contamination from the sun. That's L2. We also have L3, which is this point here. That's essentially the Earth orbit. It's like L1, but it's behind the sun. So there's a libration point there, what would be really nice to use. So it's very similar to L1. And then we have L4, which is on this side of the sun. Remember the sun, everything rotates this direction. So basically any spacecraft that would be sitting here at L4 will be seeing what the sun looks like after Earth, after it's already passed Earth. And then there is the coveted L5. And this is the L5 mission I'm talking about. And I think I'm not sure if they're exactly perpendicular, what we call quadrature with Earth, meaning complete right angle off of Earth, or if they're a little bit advanced, I forget. I think they're completely in quadrature. But L5 is essentially right here. We've had, as you can see, stereo A is slightly advanced of L5 right now. But so we know what because stereo A passed through L5 point. We know what it's like to have that. And that's an ideal spot for a monitor station, because we get about 5 days or so, maybe 7 days in advance warning of what the sun looks like before it rotates, because before the sun rotates and shows that part of its face to Earth, right? So the sun is looking here, that part of its face will rotate to Earth in about a week. So we do get a little bit of advanced warning. What I think we've learned from stereo is that the ideal place would be at L3, which is behind the sun, so we get a full backside or full far side image of the sun. However, that's an extremely difficult place to put spacecraft, because they can't telemeter to Earth. We actually had with stereo, the reason why we had this conjunction is that when the two spacecraft went behind the sun, they're trying to point their antennas to Earth to give Earth information. Well, if they're going behind the sun, that means they have to point their antenna right at the sun to try to get around it to get to Earth. Well, that will burn up their antennas, the feed horn on their antennas. So they actually had to turn during their far side passage right behind the sun. They actually had to rotate their antennas away from Earth and just go into basically a safe zone. And sadly, like I said, stereo A made it through all those maneuvers just fine. Stereo B failed when they tried to command it to do something. Something went wrong and it broke. Don't you love it? So yes, there is a mission. It won't get here till after this solar maximum. So we will be going through this solar maximum with no far side monitors other than GONG, sadly.
Okay. So we'll open it up for questions. I know it's been 2 hours here. We've been, all of her presentations are awesome. Go ahead, Mike.
Okay, thank you very much. All right, hello. Camera's up. So the last person asked a question I thought he was actually going to go in the same direction I was with the question. The stereo satellites I'm somewhat familiar with, but I am not, and I've looked for some information, and I'm probably just not looking in the right place for this. There's a current probe that's approaching the sun, and I don't know if that is the Parker probe that's there. It's a satellite that's approaching the sun right now. And what I have read in short is that it's planning to crash into the sun and accumulate some data. So my question is to you is to tell us in a simple way, because we're not scientists like you, but in a simple way, what do you expect to gather from the information of the probe that's going to crash into the sun? And is that called the Parker probe? I'm not sure if it is or not. And what is the scientific community looking for in that information?
Okay, well, excellent questions. And actually there are two probes right now, and they're actually spacecraft, and neither of them are going to crash into the sun, thank goodness, at least not in their primary mission, unless something goes wrong. So I hope you haven't jinxed it, Mike. I'm going to be very angry. I'm coming after you if they now crash into the sun accidentally. So this is a very messy plot, and I don't typically show this one, but it just happened to be handy because we just talked about stereo and Earth and everything. And so you can see Earth here at the bottom, and you can see stereo A and B in their current locations. But then you also see a bunch of other stuff. Bepi Colombo, you can see the Venus, planet. And then you see PSP, right? And you also see, if you can make it out, SO, okay? Both PSP and SO, as you notice, are very close to the sun, or reasonably close right at the moment. PSP is Parker Solar Probe. That was the one that was launched first. And SO is Solar Orbiter, okay? These two missions, Parker Solar Probe is the American mission, is the NASA mission. Solar Orbiter is the ESA mission. Now, Parker Solar Probe was launched, oh goodness, you're gonna make me think hard. I probably will get it wrong. Was it just last year, or has it been longer than that now? I think it's been longer than that. I think it was maybe launched in 2019. Please feel, if somebody knows the date, please correct me. But it was launched a little while ago now. About 6 months or so later, the Solar Orbiter was launched. Maybe 8 months later, Solar Orbiter was launched. And both of these spacecraft are getting very close to the sun. The Parker Solar Probe is going to get closer to the sun. I don't know if you can see their orbits right now, but it's showing right now Solar Orbiter is actually quite a ways out. That's the kind of the magenta line, if you can see the magenta dash line. I know it's not a great plot, but that's where the Solar Orbiter's location is right now. It's going to get in a bit closer. You can see the orbit of Mercury in here. Solar Orbiter will get in closer inside the orbit of Mercury. The Parker Solar Probe, as you can see, has a very tight orbit. That's partly because it's been able to ease its orbit down over many what we call perigee passes. I think it's still got a bit of ways to go. There's something like, I don't remember, something like 20 some odd in its primary mission. Perigee passes, it's going to make quite a few of them, and it's going to get within, my goodness, something like 5 to 7 solar radii if all works well, which is really, really tight. We've never had a spacecraft that close to the sun. Now, Solar Orbiter, I think, is not going to get anything close to that. It's definitely going to be a lot further out, but it has slightly different instruments on it. And so the two as a suite are going to answer a lot of questions, hopefully, about the sun. Solar Orbiter also is out of the plane of this plane, what we call the ecliptic plane. This is the plane where all the planets reside in. It's like a big flat Frisbee. And the sun is very different out of the plane than it is in the plane. So Solar Orbiter is actually going to get out of the plane. It's actually going to image the northern and the southern poles. And so that's going to give us a huge amount of information that we won't get with Parker Solar Probe. Where Parker Solar Probe's power comes is not only getting super, super close to the sun, but also during its perigee passes. If you're familiar with how orbits work, when a spacecraft comes into perigee, and I'm going to come here, perigee is your closest approach to the sun. So in this case, if you look at this this elliptical looking orbit, and I can't do my hand very well, but I'll try to do it around. Here's Parker Solar Probe's orbit here. And if you notice in this area where it's perigee, right here, where it goes just inside, in this really close pass of the sun, it passes very, very quickly. So the orbit, if you were to actually watch it, would go whoosh and then slow down. And its slowest point would be at apogee, which is the furthest away. And then it would slowly get faster and faster and whoosh, and then come back out and slow down. That's how it actually works. Those are Kepler's laws. But the neat thing that we take advantage of during that period is as it's going whoosh really close to the sun, it's actually catching up to the sun's rotation. And so it's going to spend a good portion of that perigee pass staring at the sun. And from its perspective, the sun isn't moving. The sun isn't rotating. It's stopped. And that is so cool because it allows us to stare at at the solar wind, at the sun emanating, the part of the corona emanating the sun, the wind out, as if you had a sprinkler nozzle. You know, the sprinkler nozzles that spin and they put out these jets of water and it looks like they're all pinwheels. When you grab that sprinkler nozzle and you stop it from spinning, the water looks very different, right? It puts out a straight jet. Well, that's what we're going to see with the sun, is we're finally going to see a straight jet of water instead of it being all pinwheeled out and spun up like that. And we've never had that ability before. And that's going to give us so much more understanding of the pristine sun than we've ever had. So that's the power of Parker Solar Probe. And like I said, the Solar Orbiter is that it's going to be looking at the sun from both the north and the south. And we've never had an imager do that before, ever. We've had Ulysses back in the late 80s and early 90s. They didn't have an imager on it, but they had a lot of instruments. And man, it taught us all about the dynamics of the solar wind, because the sun's northern and southern poles are extremely different. And it taught us a lot about the solar cycle too, because things change. And we never knew any of that stuff before Ulysses. So we're extremely excited about Solar Orbiter because of what it may offer. So both of these probes over the next decade are probably going to revolutionize our understanding of the solar wind. Everything I'm teaching in my courses and right now is probably going to be superseded by stuff that is so different. And it's just a fantastic time to be a space weather physicist because of that. Hopefully that answers the question.
Thank you, Tamitha. So how can people reach you by email? So that if they do have questions, they can just send it to you. And again, Tamitha has a YouTube channel. I think it's called Space Weather Woman, or you can search by Tamitha Skov. And she offers a Patreon service where you can actually sign up for extra podcasts and messages and all kinds of things that are really, really kind of cool. So I encourage you to visit that YouTube website, and if you're so inclined to sign up as a Patreon, I have, and it's been very good. So thank you for that. Yeah, no problem. I think we'll take one more question. We've been going here for a long time. I don't know what your schedule is, Tamitha, but you've been very patient.
I'm clear. I remember this from last time, so I don't mind. I've actually got some time, so it's completely fine. Thank you.
Any other questions?
Yes.
I think George said he had a question. Yeah, hi, George.
I have a question. Yeah, you mentioned Terminator a couple of times. Is that an optical Terminator as viewed from the Earth, or is it some magnetic phenomenon that's somehow tied to the gray line?
It's the Terminator in terms of, well, which Terminator are we talking about? Are we talking about the McIntosh et al. Terminator that has to do with the sun and the solar cycle evolution, or are we talking about the Terminator when it comes to the space weather forecast and it has to do with the Earth's day-nights, you know, the boundary between day-night? Which Terminator are we speaking?
It was part of your, yeah, it was part of your presentation earlier that you mentioned it a couple of times.
Yeah, if it's from this presentation.
You showed some diagrams that showed the Terminator at various places.
Oh, if it was from this presentation, then yes, this was the solar Terminator. So it's actually just a Terminator in time. And it's based, and I actually went into it in far more detail in my previous talk that I gave to Papa back in July. So that will help you if you want to go back to that talk. I also have talks that go into it in more detail on my YouTube channel, because I give mini courses on YouTube. But the Terminator in a nutshell is basically when we honestly believe that when I talked about the magnetic field of this, let's see, make this big. When we talk about this movie, oops, let me see if I can make it go. Here we go. When I talk about this movie and we're talking about when it opens up, it'll open up in a second, and you'll see the magnetic fields lines in the northern hemisphere and in the southern hemisphere, and how they get squished down to the equator. At the point at which the magnetic field lines of one polarity, see the blue and then the red, that polarity, once they get all the way down and they annihilate each other to the point where they don't exist anymore. See the blue and the red fading? When they fade completely out, ready? 1, 2, 3, come on, fade all the way out, well, as much as they can fade out. That right there, that is a terminator. So it's when the bands in a butterfly diagram in Scott McIntosh's thing fade out completely and annihilate each other at the equator, so that the higher bands, the higher magnetic field of the news cycle can then take over. That is when the terminator occurs. And what you see at that point is that when these high bands take over, because the low bands have finally been annihilated and they're gone, the high bands can now begin to move toward the poles. And that's when you get all the activity. That's when the sunspots come out both in the north and the south. That's when you get this huge jump in activity, is right when you hit that terminator, because it allows that news cycle. It's almost like a doorstop that you finally get out of the way, that then the news cycle can then, the door can then begin closing. And it's when the news cycle really begins to take off. So that's what I meant by the terminator in this case.
Thank you. Thank you very much.
Cool. Very welcome.
Okay.
That was a great answer.
I think what we can do is thank Tamitha, and then I'll leave the Zoom session open for people to go into the parking lot.